Good morning for all participants who's all the given by the operator in the chat.
Welcome, Dr. Adiba. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
We
Apa
just
kabar
wait a few minutes.
semua?
We wait just a few minutes until 8.
Can you hear my voice?
Yes,
Okay.
good. Yes.
Do I have to make it louder?
At the moment, it's okay. Just
Okay then. Okay.
okay. How is Malaysia? It's very hot here lately.
Okay, Dr. Adiba,
Yeah.
Mrs. Ratna, can I start the meeting now?
Okay, sure.
Yeah.
Okay, thank
Yeah.
you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Excellency Professor Dr. Widowati, SSI MSI, the Dean of Science and Mathematics Faculty of Diponegoro University, Honorable Dr. Susilo Haryanto, SSI MSI, Head of Mathematics Department, respected all of lecturers and teaching staff of Mathematics Department, and to the Honorable our speaker, Dr. Adiba Suaib, Associate Professor at Center of Mathematics Study, Faculty of Computer and Mathematical Science, University Teknologi Mara, Malaysia, and to our moderator, Mrs. Ratna Herdiana, MSc PhD, unforgettable all of participants whom I love. First of all, let's pray and thank unto our God Allah Subhanahu wa Ta'ala, who has been giving us mercies and blessing, so we can attend and gather the meeting in this place in good condition and happy situation. Standing in front of you all, my name is Mega Permatasari. I am honored to be your Master of Ceremony on this special event, visiting lecture with optimization theory and its application as the topic. As your Master of Ceremony, I would like to read our agenda in this meeting one by one. The first agenda is opening. The second agenda is welcoming speech. The third agenda is lecture and Q&A session. And the last agenda is closing. Ladies and gentlemen, before we enjoy our meeting today, let's open our program by reciting Basmalah together. Bismillahirrahmanirrahim. Thank you very much. Now we are going to our second agenda, namely the welcoming speech. I would like to invite the Vice Dean of Faculty and Science Mathematics of Universitas Diponegoro, Mr. Farihin, PhD, to deliver the welcoming speech. To Mr. Farihin, time is yours.
Mika, can you hear?
Yes, Mr. Yes, sir.
Okay.
I can.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Ya,
Waalaikumsalam.
amat berbahagia kita sapa dalam Melayu bahagia Profesor Adiba Suaib, Bapak Ibu yang berada di dalam join ini dari Departemen Matematika atau departemen lain. Okay, good morning, ladies and gentlemen. Welcome to our visiting lecture. This may please share to address our visiting professor, which is Professor Adiba Suaib, who has accepted our invitation to join us today. Professor Adiba highly accomplished in the video field in optimization. We are honored to have the Professor Adiba to us today to share her experience with our student and faculty members. Today, we will discuss optimization and its application with Professor, and we have confident Professor will be provide valuable insight and perspective in important subject. Of course, in especially our study program in master degree. Okay, we hope that this interaction will be our visiting lecture will be available experience, especially on teaching, research, and other activity of all us. Thank you, Professor. We have you with us. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Mr. Farihin, PhD, for delivering the welcoming speech. Okay, now we will move to our main agenda. But before we go into our main agenda, I will welcome all participants to turn on the camera and be ready for photo session. I will give you 2 minutes to get ready.
Okay.
Okay, I think we are ready now, so we can start our photo session. We will start for the first slide, from the first slide. Okay. 3, 2, 1. Next slide. 3, 2, 1. Okay, for the last time. 3, 2, 1. Thank you very much. Thank you very much to all participants who turned on their camera. Ladies and gentlemen, now we're going to move to our main agenda, which is the lecture by Dr. Adiba Suaib, who will be guided by Mrs. Ratna Herdiana, MSc PhD. But before that, I would like to introduce Mrs. Ratna Herdiana, who will be our moderator. Ratna Herdiana, MSc PhD, is a lecturer in Mathematics Department, Science and Mathematics Faculty of Universitas Diponegoro. She finished her undergraduate in 1988 from Institut Teknologi Bandung and hold master degree in mathematics from the University of South Wales in 1999 and hold PhD in mathematics from the University of Queensland in 2003. She has written about the optimal control of smoking program for 2 subclasses of smoker in 2023. Without any further ado, please welcome Mrs. Ratna Herdiana, MSc PhD. Mrs. Ratna.
Okay, thank you very much, Ms. Mega Permatasari, our excellent MC for this program today. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, ladies and gentlemen, to respected Vice Dean of the Faculty of Science and Mathematics, Mr. Farihin, PhD, our Head of Department, Dr. Susilo Haryanto, and the Secretary, I see her here, Dr. Titi Ujani, to my fellow colleagues, proud students, and all participants in this visiting lecture program. I welcome you all and thank you for joining in this program. And of course, a very warm welcome to our guest lecturer for today, Honorable Associate Professor Dr. Adiba Suaib from UiTM Malaysia. So I'm pleased and honored to be your moderator for this morning lecture. Going through her CV, I can imagine Dr. Adiba is has a very busy schedule. So we are grateful that she accepted our invitation. So use this opportunity to gain knowledge from her lecture today. Allow me to read her brief biography. Can you share the screen? I mean the short biography. Oh, I'll be wait. Okay. So Dr. Adiba Suaib is an associate professor of the Mathematics Department of the Faculty of Computer and Mathematical Sciences, University Technology Mara, or UiTM, in Shah Alam, Selangor, Malaysia. Her academic background, she obtained her BSc and MSc at the Old Dominion University, USA, And then she attained her PhD in mathematics and statistics, specializing in operations research from the University of Birmingham, United Kingdom in 2007. She is an associate professor of technologies at FEMA, fellow of the Institute of Mathematics and its Application, United Kingdom. She is also a professional technologist recognized by the Malaysian Board of Technologies. She was an instructor of record at Indiana University, USA for math courses at 1995 and 1994. She is also a member of the Council of Professors Malaysia, president of the Management Science Operation Research Society of Malaysia, and currently she is the treasurer of the Asia Pacific Operation Research Society. So you can see that she's active at the Operation Research Society, not just nationally in Malaysia, also regional in Asia Pacific. Next. Next. Recognition appointments. She is a life member of the Management Science Operation Research Society Malaysia and other associations. She was the Deputy Director of Malaysia Institute of Transport, MyTrans, until recently, February 23. And many administrative positions at the UiTM, including Head of Research and Publication, Head of Strategic Planning, Deputy Dean in Quality and Research, Coordinator of Quality and External Relations, Coordinator of Mathematics. Next. She's an associate professor. She's also given as a keynote speaker for many conferences and seminars in recent years. Also expert panel member for Master of Science in Predictive Analytics at UTP, University Technology Petronas. She's also external examiner for the program Sarjana Science Professional, University Technology Malaysia, advisory panel for other universities. She's member until she's still active until 2025, member of the writers team for the Higher Education Institutional Entrepreneurship Action Plan, and also permanent member of MyTrans, Malaysia Institute of Transport. Okay, next. She has supervised many PhD and master students, research projects of many master by course students. She received national, international research grants, published articles in reputable journals, proceedings, and also books. And she won, her research teams won many innovation competitions. Her research interests in the mathematical programming or optimization modeling and decision-making models involving various areas of application, such as vehicle routing problem that include e-grocery delivery routing, waste management routing, transport scheduling, workforce scheduling, machine scheduling, diet planning problems, budget planning, portfolio investments, warehouse management, facility location and allocation, network optimization, halal supply chain traceability systems, and machine learning. So abundance. research interest. Okay, so that is her biography. So, Dr. Adiba, without further ado, we can start the lecture. You have until 10 a.m. Participants can write their questions in the chat box during the lecture, and in the question and answer session, you can also raise your hand to ask directly. So I think the time and screen is yours, Dr. Adiba.
Thank you very much, Dr. Ratna. Assalamualaikum and good morning to Prof. Farhin, the Vice Dean of Faculty of Science and Mathematics di sini. Okay, and Dr. Ratna, Master of Ceremony, Miss Mega Permatasari, right? Okay, and also all professors, associate professors, lecturers, staff, and also students. Yeah. So, Assalamualaikum and good morning. First of all, I would say that it's very kind of you, Dr. Ratna, to read all the biography that I have written. Actually, you can actually just select some of them. Okay, thank you very much again for the introduction. And I would like to first of all thank the Faculty of Mathematics and Science, especially Department of Mathematics, yeah, for inviting me as visiting professors and deliver this visiting lecture talk. Yeah, I would say that I'm very happy, yeah, to be here and be able to share some experience, some knowledge to everyone, yeah. But actually, I don't know the audience whether they have taken all the mathematics subjects, whether they are in final year or in the second year or whatever. Yeah, so I hope that the contents of my presentation will be very useful to everyone. Yeah. Okay, so I'm going to start my presentation. Can you see the slide?
Yes, well.
Okay. All right. So I'm going to hold on, yeah. I would like to make sure that I have everything. All right. The topic that is given is optimization theory and applications. I'm given about 2.5 hours to deliver this. So the plan is to cover 4 topics. The first one is optimization. I hope that I can finish this in 20 or 25 minutes. And then the mathematical programming as part 2, which also I hope that I can finish this in 20 to 25 minutes. But linear programming is kind of lengthy topics, so that will take most of the time. So that will be the main focus, or many of the contents is there in this part 3, and lastly integer programming. Yeah. Okay, so with the time given, I don't think I can deliver everything, yeah, because optimization technique, yeah, was actually 1 semester course, and
Yes.
even mathematical programming is also 1 semester course, yeah. So optimization technique used to be one of the courses during undergraduate, and mathematical programming nowadays is actually one of the courses for masters in our faculty. Okay. So the learning outcomes, yeah, for this particular lecture, hopefully that after we finish this session, students will be able to identify various types of optimization problems and techniques. Secondly, to have basic and fundamental knowledge on optimization theory, models, and methods. Yeah, so I would emphasize here is about basic and fundamental knowledge. Yeah, because as I mentioned, yeah, given the limited hours, I cannot cover everything, and I cannot go into very detail. Yeah, okay. So the third one is to be able to formulate mathematical programming models, yeah, and to apply optimization theory in solving optimization problems. And hopefully that today you are able to look at some examples using optimization solver. Today I will be only using Excel. I cannot actually demonstrate to you MATLAB or some other types of solver, yeah, because of the time limitation. Okay, so the first topic, which is optimization, yeah, basically I just want to just highlight, yeah, some basic terms, yeah, and hopefully showing you some slides which enable you to recall, yeah, if you have taken all the calculus courses and so on, or some subject in optimization, maybe you can recall all those, yeah. Okay, so for those who have not taken, yeah, any optimization courses, yeah, as I said that I don't know what you have taken or what kind of courses that you have and so on. So what is optimization? Yeah, what are the optimization techniques that you know? Can you name some theories that are related to optimization? Yeah, so these are questions that you may want to ask yourself, yeah, since the topic for today is optimization. So what is basically optimization? Yeah, so optimization is, yeah, according to the dictionary, Merriam-Webster dictionary, it is an act or process or methodology of making something as best as possible or fully perfect or as effective as possible. So the term optimization itself, yeah, was actually being well known starting in mid 19th century, yeah, and the word optimize is popular to be known as to make the best or most of, yeah, certain given available resources, yeah. So optimum refers to the amount of degree, yeah, that something is best or most effective, yeah. So actually the word comes from Latin optimus, yeah, the word optimus, which means best, yeah. So when we talk about optimization problem, the goal is to maximize or minimize certain function, yeah, with or without constraints. Yeah. So therefore, the optimization techniques provide us with tools to determine these maximum or minimum values of certain parameters of this optimization problem. Thus, here, mathematical optimization involves selecting the best. Yeah. Of course, again, based on certain conditions or requirements, yeah, as specified, yeah, and optimization is not restricted to mathematics only, but it is a well-known tools or techniques that are being used or applied, yeah, in many disciplines from computer science, engineering, operation research, economics, and well, it can be actually diverse fields, yeah. And therefore, development of the solution methods for finding the optimal solution of the optimization problem has been of interest of everyone. Okay, the diagram that I have here is actually showing the constraint optimization, which is one type of optimization problem, where as you can see that we have the objective, which is the function to be maximized or minimized, and also the decision variables where they are the unknown that we would like to determine the values, yeah, which can optimize the objective function, and certain constraints that have been pre-identified, which actually dictate what kind of solution that we are going to obtain. Okay, so why do we need optimization? So it is a powerful prescriptive analytics. So when we talk about prescriptive analytics, we talk about future. It is prescribed, yeah. So it's something for the future. So that is why it is important for companies and organizations, yeah, to solve complex problems by making better use of available resources and data. So sometimes the resources are very scarce or limited, and while the data are abundant. So how do we actually use this information or use these resources optimally? Yeah. Okay. So that is the reason why mathematical optimization is so important, because it is able to capture the real world problem. Yeah. So basically you have to transform the problem into model before you can solve it using optimization solver or use some computer algorithms. Yeah. So basically you can see that this mathematical programming or optimization per se, yeah, it is very important and critical to everyone because it can lead to cost savings and revenue. Okay, I mentioned about prescriptive analytics. As you can see with the degree of optimization here, yeah, from descriptive to diagnostic to predictive and prescriptive. Yeah. So as you can see that descriptive is just describing what is currently happening. Yeah. Whether it is in terms of graphs or some summaries or information or analysis. Yeah. And while diagnostic giving us the capacity of getting deep understanding of certain things, while having optimization and prescriptive analytic will be actually providing us or offering us with a means to be able to foresee the future in terms of what should be produced or what should be the things to happen, yeah, or the resources that must be made available and so on, or must be produced in order to meet certain demand or certain requirements of the future, for example. So if we have just now only 4 levels of analytics, we can actually have more, yeah, by adding cognitive analytics, yeah. So we have descriptive, diagnostic, predictive, prescriptive, and cognitive, yeah. So this is an example how it can be utilized in business, but the key idea here is the optimization, yeah. So the optimization is being the a key or the critical element that allows people to make the right decision or the best decision. Okay, now let us look at the classification of optimization problems. Yeah, so the optimization problems can be classified, yeah, in many ways. First is based on the constraints or without constraints. So we can have unconstrained versus constrained optimization. It can be because of the design variables, where there is a static or dynamic optimization problem, whether it's the physical structure, optimal control or non-optimal control, the nature of the functions in the models, whether it's linear or non-linear, whether you have quadratic or geometric. Yeah. And then we have the permissible values of the variables. Because of the categories or the types of variables, yeah, specification of the variables, it falls or it actually divide this or classify this into several types of mathematical programming models. And also we can have the deterministic nature versus the stochastic nature. So we have stochastic or deterministic programming. Or is it in terms of the separability? We can have separable programming or non-separable. And also it can be due to the number of objective function, be it a single objective function for the mathematical model or multiple objective. Yeah. So this is a little bit of description of optimal control problem. Yeah, so it involves number of stages. Yeah, in certain prescribed manner, but here the most important thing is the types of variable. So we can have the control or design of the states variable, which define the system and govern the evolution of the system from one stage and so on. Yeah, so this is just a little bit of or highlights of the optimal control problem. And we can also have geometric programming. Yeah, so the geometric programming is where the objective function is expressed as polynomials, not polynomial, yeah, polynomial. So we have description or example here on what is polynomials, yeah, okay. And then in terms of basic structure, we still have minimize or maximize certain function subject to certain constraint. The same goes with quadratic programming. It is just simply because of the existence or the presence of quadratic function within the objective function or maybe the constraints. We also have stochastic versus deterministic, where stochastic programming involves the weights to be actually some probability. Therefore, we deal with certain probability distribution. While deterministic model or deterministic programming, we can say that it uses number as input and output. Yeah, so it is fully determined. Yeah, or the parametric values and initial condition are known. Yeah, so in other words, it's not like the probability. It is actually deterministic outcome where it is risk-free. Okay, and as for separable, yeah, the separable programming is one in which the objective function and constraints are separable. Yeah, so you can read further on separable programming function. Multi-objective means that we have more than one objective functions that we would like to optimize. Yeah, we can have series of minimization of functions, or we can have a combination of maximization and minimization. I put an example here. Yeah, you can have maximize certain things, minimize certain things subject to certain constraints. Yeah, so because of the nature of this multi-objective, normally we use code programming technique to solve this multi-objective programming problem. Well, to summarize the definition of terms, again, optimization means you optimize, that is minimize or maximize a real function. Unconstrained means no constraints are imposed on the decision variables when optimizing. Constrained optimization is where the solutions are determined by optimizing the objective function subject to certain constraints, where the objective function, on the other hand, is the function that you want to maximize or minimize. So this is the structure of constraint and unconstrained optimization. Yeah, so you can see clearly we have minimized, maximized. For unconstrained, no constraints at all, but constraint optimization, it is the optimization of the objective function is subject to certain inequality constraints or equality constraints. So I put a note here, constraint optimization problems are generally a lot harder or more complex to solve. So I put also here types of constraints. Yeah, when we are modeling the problem or optimization problem, we might want to prepare or to identify the behavioral constraints, which means that you must know the limitation or specification or the behavior of the system or whatever problem that you are dealing with, aside from the site constraints, which represent the physical limitations or requirements. Okay, we can also categorize the constraint as hard or soft constraints. Hard constraints mean they must be satisfied, must be adhered to. So no violation is permitted. But for soft constraint, the soft constraints can be violated, but on the cost of penalties. Yes, certain penalties will be imposed to the decision variables that cause the values of the objective function to be affected. For the scope of this lecture, yeah, I basically concentrate on constraint optimization, yeah, and mathematical programming models, yeah. So with the time given, I will focus on linear programming and integer programming particularly, yeah. So note that the term program here is not algorithm or coding, yeah, in computer program. It is basically the strategy or decision rules or certain structure, yeah. So mathematical programming is therefore, yeah, is a kind of decision program, yeah, where you are able to produce solutions in structured manner. Okay, let's look at history of optimization, yeah. So the history of optimization is long, yeah. Sorry that I missed the I there. The history of optimization is long, yeah. So it started with the mathematician Bernoulli, Lagrange, Euler, and Weierstrass, yeah, who developed the variational calculus. Yeah, that was the starting, yeah, the starting of the optimization, where the notion of optimality, yeah, is on finding optimal solution, and that is developed during the same era as these mathematicians, yeah. And who were involved, basically, yeah, the optimization was actually part of operation research, which is decision problems, which actually encountered during the World War II, yeah. So where British and the Americans are actually trying to solve complex problems during the fight with Germans, yeah. So here they actually needs to make sure that they have optimal strategies, yeah. Okay, that was when we have the scientists being included, yeah, in this effort, and one of them was George W. Danzig, yeah. So if you recall, Danzig was responsible to introduce simplex method for solving linear programming problems, yeah. Besides that, we also have John von Neumann, yeah, in 1920s, yeah. And also we have Albert W. Tucker. So these are among the people who actually responsible, yeah, for the optimization and mathematical programming. So here are the yeah, photos of these mathematicians, Isaac Newton, Leibniz, Lagrange, Cauchy, and also Euler. So you can see the topic here, calculus methods of optimization, yeah, basically at the starting era, yeah. And then we have followed by, yeah, in the 19th century, we have Danzig, yeah, for the simplex method, Richard Bellman for dynamic programming, von Neumann, known for game theory, and we have Karushkan Tucker, if you remember, or some of you maybe have gone through the optimization techniques courses, yeah, where we have this as part of the necessary and sufficient conditions for optimal solution, yeah. So I don't want to be actually discussing in lengthy in terms of unconstrained optimization, because I'm sure that everyone has taken calculus, yeah, hopefully, yeah, even the undergraduate students, because the calculus mostly comes at the beginning of your study. So I hope that you already have encountered, yeah, certain types of optimization, yeah. For example, here, how do we differentiate between root finding and optimization? Yeah, so there is a difference. Root finding is where you are finding zeros of function. Yeah, you set the function equal to 0. Yeah, but optimization is where you find the minimum and maximum of the function. Namely, you are relying on the first and second derivatives. Yeah, so these are some rules that you are familiar with, in deciding whether a particular critical point is local max or local mean, whether it is a global max or global mean. So these are the rules that we actually use, in terms of deciding whether you have absolute maximum or minimum, or global max or global mean, or just the local max or local mean. Okay, these are familiar analysis when we are deciding whether critical points is a local extremum or whether it's inflection point. And for example, in this one here, we are deciding what happens to the critical point, and then we are deciding whether it is actually local max or local mean. So this, I think you are familiar with. From this, we make certain analysis in terms of first and second order derivatives. And finally, we can summarize all the information and be able to sketch the graph and identify local max or local mean and global max or global mean if they exist. For this particular example, it's just having local maxima and local minima, but no global optimum. Okay. So here, this is an example, another example where you can find absolute or global minimum. Okay. The optimization, especially of function in one variable, as you have encountered in calculus, for example, is applicable in solving real-world problems. For example, this farmer would like to fence certain rectangular plots, where part of the border is a straight river. So there are many possible ways, but in general, when you want to solve, you have to present this in terms of equation, because from the equation, then you can find the derivative, and make further analysis to decide whether we have maximum, minimum at certain critical point. Okay, so this is just example. And we can also have maxima and minima, of functions of two variables. Of course, we have to make sure that we find necessary information for us to be able to decide whether we have relative maximum or minimum, or absolute maximum or minimum. Okay. So we have definition and theorems that will guide us toward making decision whether we have the maxima or minima of this function. So this is just to show you how the definition and theorem can be applied in having us deciding the answer to the problem. So this is a function of two variables, starting by finding the critical points, as you can see here, and then based on the critical points, we make analysis, or we come up with the analysis in terms of the critical point based on whatever the theorem actually has outlined for us. And finally, we are able to decide whether we have relative max or minima, or whether it is a saddle point. As I said, that I don't want to discuss in detail. Okay, in general, if you have function of several variables, you can start by finding the gradient and also the Hessian, and then use certain guides here to decide whether you have a local max or local mean. So here, this is an example where we can see that we have at 3 and -3, we have this point as a local mean, by following the steps that have been given or outlined for us. Okay. And finally, we have the constraint optimization, This is all calculus part. Yeah, I haven't gone into mathematical programming model yet. Yeah, so it is constraint optimization, multidimensional. That means we have several variables, x1 until xn, subject to certain constraints, whether it's inequality constraints or equality constraints. Yeah, so here we have this structured steps. Yeah, but first of all, you must be able to come up with the Lagrangian function. Yeah, you must come up with this Lagrangian function before you can find the partial derivatives and use the Karush-Kantaka or Kantaka condition. Yeah, Kantaka sometimes is also known as Karush-Kantaka or KKT or KT conditions. Yeah, so these guide us on the steps to be taken in deciding whether we can find the minima or maxima. Yeah, so the Karush-Kantaka condition is necessary and sufficient condition, which actually tell us whether the objective function is differentiable and concave, whether the function g(i)(x) in the constraints are differentiable and convex, and so on. Yeah. Okay. So this is an example of constraint optimization using Lagrangian. Sorry for the misspelling. I put function, but I type FUND. Yeah. Okay. And then we have this example of application on the utility function. Yeah, the utility derived on exercises and watching movies is given as this one is to relate the exercise and watching movies. Yeah. And then what we have here is we apply, get the Lagrangian function, get the first order condition, and then by substitution and so on, solving these equations simultaneously, we are able to get the optimal solutions. Yeah. Okay. So I think that is the first part that I would like to present, part one on the basic ideas of optimization. I don't know whether I can actually ask questions or not, but well, I don't need you to answer, but I just want to ask you to think about it. Can you name 3 types of optimization problems that I have shown in the slides? Can you do that? Can you recall 3 mathematicians who have contributed to optimization techniques? Yeah, these are just, Dr. Ratna, I just want the students to think about it, yeah?
Yes.
Okay.
They can try answer and write on
they can try to answer, all right, yeah? So, and then, do you recall the type of analytics which actually represent the highest level of optimization? Okay. And what's the difference between linear programming and non-linear programming? Did I mention that? Okay. All right. If I have not mentioned, then I will mention it later. What signifies the difference between linear and integer programming? Just now, linear and non-linear model. Now, how about linear and integer? Yeah. How to solve the multi-objective programming model? Okay. Do you remember the term? Okay. What is the difference between root finding and optimization? Okay. And you may want to try to fill in the blank. When the second derivative of a function of one variable greater than or equal to 0, fx is a convex function. Then the local blank, which is x star, or is the global y of f of x. Okay, and then if a function of 2 variables has absolute maximum or minimum at an interior point of the domain, then the extremum must occur at what or where? Yeah. And last one, KKT for constraint optimization is the for optimum solution. Okay, these are just to highlight to you. Okay. All right. So that is actually the first part that I want to show you. So I will continue with the second part. Then after that, we have a break. And then we will do the third part. Yeah, the third part is the longest one. So we will take certain minutes. Yeah, and then we do the third part. Yeah. Okay, let me just continue. Is it okay, Dr. Ratna? Just continue with the second part?
Yes, doctor.
Okay. Now, the second part is on mathematical programming. Yeah. So I hope that I can go over this quickly also. Okay. What is mathematical programming? Yeah. So just now I mentioned about unconstrained. Yeah. Unconstrained optimization. So basically mathematical programming, yeah, is for constraint optimization. Yeah. So as outlined, this is part 2. Yeah. So let us know further about mathematical programming. Yeah. So what are the types of mathematical programming models that we can have? What are the general properties and what methods can we use to solve the mathematical programming models? Okay. All right. So here we would like to get a little bit of background and the structure or main components of the MP models and also the solution method. Yeah. So what we have here is that we relate mathematical programming with operation research and analytics. We would like to know the basic structure and main components of MP model and also classify, yeah, the types of mathematical programming model. Yeah. Okay. I mentioned already that MP is strongly related to operation research and also management science. Yeah. Well, in Europe, it is widely known as the operation research, but for US, it is popular with the term management science. Yeah. And then mathematical programming, especially linear programming, I think is widely known. Yeah. Especially for us who actually take mathematics as our degree, definitely you come across operation research. And mathematical programming have been used, yeah, for business and other fields, yeah, even engineering, yeah, and all sorts of areas, yeah. So what we have here is that, yeah, the important terms that are being actually emphasized in operation research is modeling. Yeah. So what we have here is that, yeah, analytic is the one that has the highest degree of abstraction and being complex. Yeah. So here we look at the relationship between mathematical programming and analytics. Yeah. So I have mentioned, yeah, I have highlighted, yeah, the learning analytics and where mathematical programming or optimization being the critical part or the one that has higher degree of analytics. Yeah. So just let us look at again the types of analytics: descriptive, diagnostic, predictive, and prescriptive. So the optimization is at the part of the prescriptive, yeah, analytics. Okay, so let us look at the components of mathematical programming models. Yeah, we know mathematical programming models widely used, and we know about the word program is not computer program. And when we talk about model, it is the abstraction or representation of problems, yeah, into, yeah, mathematical symbol and also, yeah, certain equation or inequality, yeah, to represent the relationship of the system, yeah, within the system. Yeah. So we can have equation or inequalities, yeah, as part of the mathematical programming model. And here I emphasize again, programming is not computer programming, even though we can actually use programming to get the solution. Yeah, tetapi per se, yeah, it is not the types of programming or coding. Yeah, so the word programming is more of the structured approach, yeah, in solving, yeah, problems. Yeah, but the most critical components here is the decision variables, yeah, constraints, and the objective function. Yeah, number 5 here. Okay. So therefore, yeah, when we model mathematical programming, make sure that we define the variables, especially the decision variable. What are the constraints? What are the parameters? And for the parameters, we need to know the coefficient of these parameters because they will appear especially in the objective function. Yeah. Okay. This is the general structure of a mathematical programming model. Look at here, we have decision variables must be defined first. It is a vector. Objective function, we minimize or maximize certain function. And we must put our list out the constraint subject to what. Yeah. And then, sorry that there is animation here. Yeah. Saya kena bercakap according to the phase of this animation. Yeah. Okay. But here, do not forget that when you write down the formulation of model, you must emphasize the non-negativity constraint, especially for linear programming. For some other types of programming, you must specify the domain of decision variables. Yeah. Okay. Now, let us look at types of optimization problems or optimization models. The main one is linear versus non-linear programming. How do we know is linear programming model or non-linear? It is just a matter of the types of functions that appear in the model. If all the function in the constraint and objective functions are linear, decision variables are real numbers, then it falls under the category of linear programming. The minute you see any function which is non-linear, it goes under non-linear programming. How about integer versus linear? Integer is due to, integer programming is part of linear programming. But what's the difference? The difference is in terms of decision variables. In integer programming, we expect that all or partially, or some of the decision variables to be integer. So therefore, we can have binary integer as part of decision variables or pure integer in the decision variables, or you can have a mixture of binary with a real number with integer. So therefore, we have mixed integer. If we just have binary 0, 1, we have binary integer programming. If we just have integer, pure integer, we call it pure integer programming. Well, this is the classification. You can see the difference between linear integer, mixed integer, quadratic, semi-definite, quadratic constraint program, and also convex programming. Hilang pula dia punya ni, short form, non-linear programming, constraint programming, and so on. So these are the characteristics or the nature of this linear programming problem that differentiate one from another. Okay, next, we know that we have constraint optimization. General form is to minimize or maximize certain objective functions subject to constraint. We already know that it is important to define the variables because, and then also set the constraints because, because what we have here is that the constraints will define the set of feasible region or set of feasible solution. Okay. And then if the feasible region is empty, then we cannot find solution. If it is not empty, then the LP, linear programming, is consistent and solution exists. And also, there is a situation where we can have no solution, unique solution or one solution, and alternative optimal solution or multiple solution. For unconstrained, you are familiar with this during calculus time. And then, this is for the unconstrained. Saya tak payah, I don't need to talk about this because I already mentioned it earlier. Okay. All right. Now, let us talk about the graph of linear programming problem in 2 decision variables and more. In two decision variable, in two-dimensional, we have a two-dimensional, a two-dimensional graph like this, and we basically determine the optimal solution using graphical method. Either we use the isoline method or corner point methods, to get the optimal solution, Whereas in the multiple variables or two or more decision variables, we can end up having polytope, polytope, this kind of three dimension, where you have to search for the optimal solution, starting from initial solutions through investigation and search procedures, you have the optimal solution. So these are just illustration of the graph or the type of feasible region that you will get, for the LP problem with two decision variable and more than two decision variables. Okay, let us look at here, further illustration of linear programming in 2 dimension and linear programming in 3 dimension. So here you have, basically, the isoline, as part of ways for you to determine the optimal solution. In 3 dimension, we use the plane, as part of the process to determine the optimal solution, which is dictated by the feasible region in polytope form. Okay, so what's the difference between integer programming and linear programming? Come again, it is actually because of the specification on the type of decision variables. We can have purely integer values or a mixture of binary or integer and real number. If it is purely 0, 1, for the values of decision variable, we call it binary integer programming. Okay. So if you look at the difference in terms of the graph, yes, we see the feasible region, but the feasible points are these dots only. Because why? We are concerned about getting the solution to be integer values. For example, if you talk about integer programming problem, so these are pure integer. So you have to make sure that it is no longer including all those continuous values, with decimals or fractions, just the integers, if you talk about pure integer programming. And then, note that later we will discuss about, you cannot simply round off values that you got from linear programming problem. When we solve linear programming, we expect that the answers are or the solutions are in real numbers, so they got decimals. So for problems that require integer solution, can we simply round off the value? So that will be discussed later. Now let us look at the quadratic programming. So this is the solution method, in terms of how we approach to the optimal solution, local max or local mean in the quadratic programming. Okay. Now, okay, in terms of optimization, convex and concave are still the main elements that we have to inspect, whether the nature of the graph, is convex or concave, So that is why it is very important to understand what does it mean by convex, Okay. Now, to summarize, we have linear, non-linear, integer, quadratic, and also convex programming, just to name few of these mathematical programming classification. So, beside those, we also have semi-definite programming, stochastic, robust, dynamic. These are all parts of mathematical programming model. And the terms like combinatorial optimization, trajectory optimization, constraint satisfaction problem, and infinite dimensional optimization. Yeah, these are actually terms that you may encounter when you deal with optimization. Yeah. Okay. Next. Okay. So this is the last part of this part. Can you explain the structure and the main components of mathematical programming model? What are the main components of any mathematical programming model? Can you recall? Okay, all right. And can you relate? Yeah, number one is actually, can you relate mathematical programming with operation research and analytics? Yeah, how they are associated? Yeah, the mathematical programming, operation research, and analytics. Yeah, and then can you explain the structure or main components of the mathematical programming model? Can you identify the types of mathematical programming models? Yeah, how many can you recall? I have shown a few types of mathematical programming models. Can you name few of them? Yeah, so if you are able to answer question 1, 2, and 3, or at least, yeah, you can actually remember some of those. Yeah, that means you already understand, yeah, about, yeah, basic or fundamental knowledge related to mathematical programming models. Yeah, so we see the family of all these models as mathematical programming model, MP models, and we have these divided between linear and non-linear. Yeah, and we can have, under linear we can have pure integer programming, binary integer, or mixed integer. And also the classification can be extended to whether you have deterministic model or stochastic, yeah, programming. Yeah, and well, we have mentioned in the first part, yeah, it can be yeah, due to many reasons, yeah, where we can classify the mathematical programming models into different types. Yeah, it can be because of the type of, yeah, variables, the types of function, yeah, whether it's optimal control or not optimal control, stochastic or deterministic, and so on. So these are actually the reasons for us to have a different classification. Okay, so that's the last part of the part 2 on mathematical programming. Yeah, mathematical programming. So Dr. Ratna, can we have, yeah, can we have break, yeah, for maybe
break,
10 minutes
yes.
before we continue with the third part on linear programming? I hope it's okay.
Yes, yes, I think that is possible, Miss Mega. So while the students try to answer the questions also.
Oh, really?
To recall,
Oh, very
yes.
good. Yeah. Okay.
Very-
Yeah, but I so
We
sorry
can
that I did
have
not
a
provide
quick break.
the PowerPoint earlier on. Yeah. Okay. But I hope that they get some basic ideas about optimization and mathematical programming to start with. Yeah. So maybe we can have a break.
Yeah.
Maybe how many minutes?
Yes.
You think?
Miss Mega, how many minutes how much you need, doctor?
Yeah. 5 to 10 minutes is okay.
Okay.
5 minutes maybe.
5
Yeah.
minutes?
Mm-hmm.
Okay.
Is it okay?
Okay, it's good. Yes.
All right.
Okay. Miss Mega, we will have a 5 minutes break. Students can try to answer the questions. Okay, Dr. Ariba, you can have a break for 5 minutes.
Okay, can you see the questions?
Yes,
Yes. Yes.
ma'am.
Okay. Did you get the question? Maybe snapshot the questions.
We can see it, Doctor.
Okay, you snapshot the
clear.
question, okay?
Yes.
All right. Is it okay if we continue?
Yes, doctor, we can continue.
Dr. Ratna or Miss Mega, can we continue?
Yes, doctor, we can continue.
Okay, thank you. Okay, I will continue with the third part, which is on linear programming. Okay. Okay, everyone, welcome back. Yeah. So I'm going to continue the lecture, yeah, with the topic of part 3, which is linear programming. Yeah. So under this topic, I will talk about the fundamental theorems of linear programming, the model formulation, and also the applications, in this case, solving the linear programming problems. Yeah. Okay, maybe I just change a little bit on the fundamental theorems. I put this at the end. Yeah. Okay, so hopefully, inshallah, yeah, at the end of this lecture, you should be able to describe how you can write the linear programming model, yeah, how you can actually, yeah, instead of given the problems and you transform it to formulation, you can also actually start by given a graph and then you formulate the linear programming model. That can also be done. Okay, so next is how to solve this using the graphical method, and how to solve this using the Microsoft Excel as our optimization solver, and what kind of interpretation or analysis that we can come up with, yeah, with the solutions obtained, and then how we can conduct sensitivity analysis on the solutions of the linear programming problem. Okay, first of all, yeah, when we discuss about mathematical programming model just now, we already know the structure of any mathematical programming model, which should include the definition of decision variables, yeah, formulation of the objective function, and then defining all constraints, specifying the decision variables or putting the non-negativity constraints, and then we should be able to solve the model afterwards. Yeah. Okay. So here, the modeling process involves identify what problem you are dealing with, then formulate the model, analyze the model, test the results, and implement the solution. Okay. Before we get so excited in modeling, yeah, there are a few assumptions on the linear programming model. The first one being the parameter values must be known with certainty. When we say parameter values, such as, yeah, the certain things that being coefficients or input data for the model, yeah, they must be known in advance. We must know them. For example, if we would like to talk about scheduling workers, we should know the number of hours, yeah, at most they can work per day or per shift, yeah, for example. Okay, next is the objective function and constraint exhibits the constant return to scale, the proportionality. If one unit costs this much dollar, so if many units, you just multiply this with this amount or this cost, yeah, for example. There are no interaction between decision variables. Therefore, we have the additivity assumption. Yeah, so you can have how many x1 plus how many x2 and so on. Yeah, and then we have continuity or divisibility assumption. Yeah, decision variable can take on any real number value. Because we talk about linear programming, the types of decision variables, they are actually belong to the set of real numbers. Yeah. Non-negativity, yeah, for linear programming problems, because we are dealing with real world problem, yeah, we shouldn't be getting answers for negative values, yeah. For example, if we are solving real problems, yeah. Therefore, values of decision variables are non-negative values, yeah. Sorry, ni 2 kali, ya, terulang ni. Sepatutnya ni tiada, ya. Non-negative values of decision variable. Okay, sorry. I see the reason why. Yeah, sorry, I didn't realize this just now. Okay, since the values of decision variables are non-negative, therefore negative values of decision variables are unacceptable. So that is what I wanted to say. Yeah. Okay. So, for example, we deal with the simplest version of linear programming model, which is a function of two variables, x and y. Yeah, we have a and b coefficients of this the variables in the objective function and also the constraints. Yeah. So the value of x and y will become the decision variable or values or the solutions. Yeah. So here, when we specify the constraint will actually identify the feasible region. Yeah. And what do we know as the optimal solution? It is the choice of values of x and y which optimizes or maximizes or minimizes the objective function. So that will be the optimal solution. Yeah. So for graphical solution method, we have two choices. Either we use isoline method or corner point method. Basically, these two methods requires you to draw the graph first. Yeah, the graph of the feasible region. Yeah. Okay, then we select a specific profit or cost line. This is actually the objective function line. Yeah, and graph it to find the slope. Yeah, and then for the other part, yeah, corner point, the name itself is describing that you must identify all corner points. For isoline method, the solution is found by shifting the line that you draw for the objective function upwards, downwards, towards left, right, upward, or down, left, downward, and so on. Yeah, by shifting the isoline or the objective function line, yeah, we are able to get the optimal solution. The last point touched by the feasible, by this line will be the optimal solution. Yeah, and then we can determine the value of the objective function at this point. Yeah. As for the corner point method, after we identify the corner points, we actually tabulate these so that we can actually evaluate the objective function. Okay. And then we select the corner point which represent the best value of the objective function. If we are maximizing, choose the highest value. If we are minimizing, choose the smallest value. Okay. So the fundamental theorem of linear programming stated that if there exists optimal solution, it must occur at the corner points or vertices, yeah, that located, yeah, at the perimeter of this feasible region. Yeah, in the case of unbounded region, yeah, okay, then a maximum value for the objective function may not exist. Depends on the objective function. However, if it is unbounded and the objective function has only positive coefficient, then you may find a minimum value. Yeah. Okay. So in general, we can say that a linear programming problem can have no solution, unique or just exactly one solution, or you can have alternative optimal solution or alternate optimal solution or multiple solutions. Yeah. So in other words, there are three possible cases: no solution, a unique solution, or you can have alternate optimal or multiple solution. Okay. Now, what is the characteristic of the feasible region? The feasible region is actually determined by all the constraints. The intersections of the constraints region will actually determine the feasible region. Yeah. What is the corner point? The corner point must lie at one or more corner points of the feasible region that you got. Yeah. The corner point with the best objective function value is optimal. In multiple dimension, the region of interest is of higher dimension, like this lah. Yeah. So this is a polytope. Yeah. Okay. So polytope is a polygon in higher dimension. Yeah. A geometric object with flat size. So it is actually bounded by certain planes. Yeah. Simplex, a generalization of notion of a triangle of tetrahedron to arbitrary dimensions. So simplex actually later on will be describing on how we can use the idea of simplex in order to determine the solution. And for algorithmic method, yeah, optimal value will always be on the vertex of the polytope. So if we dealing with higher dimension, you can see that these are the the vertices, yeah, at the corner of this region. Yeah, so these are the vertices. So basically you are searching by evaluating or investigating or checking each of these vertices. Okay. Now, there are special cases in graphical method. One is called redundancy. Redundancy is where you have extra constraints, which actually doesn't play any significant roles. Yeah. With or without it, we still have the same feasible region. Yeah. So this extra constraint is not influencing or affecting the feasible region that we obtain. Unboundedness refer to, yeah, this feasible region being unbounded. Yeah, unbounded. So we cannot actually restrict the parameter of this feasible region. So certain part is being unbounded. Infeasibility, when the model has no feasible point or no feasible region, an alternate optimal solution occurs when you get more than one optimal solution. Yeah. Okay. Now, the first case is redundancy. So we have redundancy, for example, we have certain constraint, then, yeah, sorry. Okay. You can see that we have three constraints, namely, but we got this feasible region. The last one, x1 less than or equal to 25, it is not actually of any use. Because why? We're still getting the same feasible region. So this is extra constraint which does not affect the feasible region obtained for the solution. Yeah. How about unboundedness? How does it look like? Yeah, this is an example where the feasible region is unbounded on the right. Yeah. So in other words, the feasible region is being not bounded in certain part. Yeah. And then we have infeasibility. Infeasibility refers to a situation where when you plot the region for the constraint, suddenly you end up having many components where there is no intersection between these components. Yeah, so you have this part and this part, so no intersection of at all. Whereas we know that the feasible region is intersection of all constraints. So there is no intersection, no feasible region. We cannot find the feasible region. Thus, we cannot find feasible solution. Okay, alternate optimal solution is just the case of where you can have multiple solutions. In this case, for example, if I move or shift this isoprofit line here upwards, because this is maximization, for example, you end up these to be identical or overlap with one of the boundary lines or the parameter of the feasible region. So that means any point, any real number in between A and B are optimal solutions. So you have, well, infinitely many solutions. Yeah. Okay. Now, okay, for example, here, if we look at the graph, yeah, and apply, for example, the isoline method, yeah, you can see that, for example, this is a bounded feasible region, yeah, where you can apply isoline method or corner point method, yeah. For example, I put here the red color is the isoline. Yeah, if you shift upward in the case of maximization, you are going to obtain, yeah, the maximum value of the objective function equal to 15, where 0 or 3 is the optimal point. Yeah, optimal point. Yeah, the last point touched by this isoline. For the unbounded region, in this case, what should be the answer? Yeah, where we shift this objective function line or the iso line, yeah, to the right upwards here, yeah, what do we get? Is there any last point being touched? Do we get a feasible solution? What do you think? I mentioned about what happened if you are maximizing unbounded region and so on. What happens here? Yeah, so that is one characteristics, yeah, and or special case in linear programming. And we can have this feasible region, but we have redundant, yeah, constraint, yeah, one of these like this one here is redundant. And then what's the solution? What's the solution here? Yeah, so this is just to give you some ideas, or this to illustrate to you, yeah, how easy for you to actually identify whether or not we have a solution, whether there exists one solution, or whether there exists alternate optimal solution. Yeah, for example here, yeah, this is unbounded, but this is a minimization problem, which means you are shifting the iso line to the left downward, for example here. Yeah, so does it have solution? Yeah, so in this case, what we have is we have alternate optimal solution, because this line is being, yeah, overlapping this line of 5x plus 4y equal to 40. And what we have here is that whatever along these 2 points, including these corner points, they are all the solutions or optimal solutions to this problem. So what we have to do is we find the general solution representation. Either you set the x arbitrary. So first of all, you look at which line affected or involved is this line of 5x plus 4y. So what you have to do, you can decide whether x arbitrarily or y arbitrarily. Yeah, so if you let x arbitrary, just write this equation in terms of x, yeah, y in terms of x, and then, yeah, there is a constraint here. The value of x must be in between these 2 points. Yeah, so if you solve for x by having yeah, solving the simultaneous equation for x plus y equal to 16, and also 5x plus 4y equal to 40, and also the line x plus 5y equal to 20 and 5x plus 4y equal to 40, you will get these 2 points, and then you can see that the values here, yeah, applies. It is between 2 point something to 5 point something. Yeah, so any value between 2 point something to 5 point something here, yeah, will do. Yeah, can be candidate solutions. Yeah, can be solution. And then you evaluate the y given by this 40 minus 5x over 4. Yeah, you can get that one. Okay, now when we have linear programming model, what is the reason why we formulate the model? Because we want to solve problems. Yeah, when we want to solve problem. So before we can solve the problem, we have to understand the problem, and we must do certain things. Yeah, there are certain steps. First, understand the problem. Then decide what are the decision variables, what are the constraints, yeah, and then what are other restrictions. So you have to read line by line, yeah, and then identifying and so on. So this is the case of, this is toy company, yeah, toys company producing 2 types of toys, and then there are certain things, a lengthy paragraph. Okay, you have to summarize. Yeah, summarize. So question here, would a different production schedule improve company profit? Yeah, you just imagine, it's like 1 page problem. Yeah, and then you have to understand it. So it is important for you to summarize what information do you have. Yeah, So for example, there are 2 toys, resources limited, 1,200 pounds of plastic, 40 hours of production time, marketing requirement, total production cannot exceed 800 dozens, number of dozen of space rays cannot exceed number of dozens of zappers by 450. So we list down all the requirements, yeah, including the technology input, the coefficients, okay, and also, yeah, producing as much as possible, blah, blah, blah. These are actually affecting the objective function, okay. Now, this is the model that we come up with, yeah, number of dozens zappers, number of dozens space rays, yeah, because we want to know how many dozens to be produced, yeah, so the profit is 5x1 plus 8x2, subject to plastic constraint, production time constraint in hours, production total, production mix, and non-negativity, yeah. Just to highlight here, I put a note: when you draw a feasible region, be ready to note that there are some corner points, yeah, interior points that includes, yeah, corner points, interior points, yeah. Extreme points are the corner points, and then the interior points, the green color here, consists of the interior points. The boundary points along all the lines, which are being the boundary of this region. Extreme points, the black dots here, okay. And then that's how we actually work it out. You can use 2 methods. One is you can identify the corner points, evaluate the objective function using all these, yeah, a pair of coordinates x1, x2, yeah. Or you can use the ISO line. What is the ISO line? You select a arbitrary value for the objective function z here, and then there you get an equation, plot this equation over the line, and then plot the line. And the next thing is, depending on whether maximization or minimization, you can shift upward or downward and so on, okay. And here what we have is that, yeah, if we are using corner point method, we just tabulate these corner points, evaluate. The highest value is 5040. That is when x1 equal to 240 and the value of x2 480. That is corner point method. But for ISO line, you can do not do both, one only. You can use corner point or ISO line. Yeah, for ISO line, you just actually do this, yeah, and then you have this yeah, shifted upward. Okay. All right. So how do we carry out the sensitivity analysis? The easiest way is that, yeah, the sensitivity refers to what if. You already obtained the optimal solution. What if you change these? What if you change the constraints? You change the coefficient of the objective function. You change the value of in the technology matrix, and so on. Yeah. So these are sorts of the analysis of post-optimality analysis that you want to answer. What happens? Yeah. What happens if you change that? Okay. Now, so I hope that, yeah, later I will use this in order to get the solution, yeah, for the Excel, yeah, data, yeah. Okay, now let's look at here, yeah. Or you may also want to try on Excel. I don't know whether you have done Excel or use Excel solver before, yeah. Okay, very easy. Later, if I have time, I show you. And then we have here, yeah, another types of problem, the same types of steps. First, identify what are the decision variables based on the information. You must know what is the parameter that you want to optimize, in this case, profit, yeah, and what will be the equation for this profit. You know that one chair profit, one chair is $5 profit, and then table murahnya, yeah, this is too small, yeah, maybe I should put 50 and 70, yeah, so that is more profit, yeah. So this one just 5 and 7. Okay, so we have 7 T and 5C, yeah, subject to what are the constraints in terms of available hours and also the quantity, yeah. Okay, and I think I missed 1 0 here. ya. Sorry for that, ya. Bila nampak di sini, sorry, 100, 400 itu okay, this okay. 1000 is actually a mix. Okay. All right, this one correct. Yeah, this one correct. 2400, 1000, and then 100. Okay. Then after you get those, you can enter this in the Excel solver. Okay. I hope that I can demonstrate this to you, yeah, in the Excel solver. First, I would like to ask Dr. Ratna or maybe Miss Mega Permatasari, how these students, yeah, do they have they taken any linear programming? Yes,
Yes,
no?
we have linear programming course.
Have they used Excel solver?
Who is taking linear programming?
I think, but
Because I don't know the students there.
Adakah yang ambil linear programming? Raise your hand.
saya ngambil Bu.
Belum.
Sudah.
Sudah. Do you use
Sudah.
Excel solver?
We
Excel
don't use
solver?
Excel.
Tak pakai tangan saja, manual.
Okay,
Yes.
okay.
Yeah.
So let me just demonstrate because this is a very simple one, yeah. So I can do this quickly. Okay. Let's just do this one first. Okay. 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 So what you need to do is just set up these cells for us to enter the input. I hope that you can see. Sorry, it's too big. Okay. You can see the input here. Let me just make this a slightly bigger. Okay. So I just put here the variable first. I must prepare the variable. Let me just make the variable larger. Okay, the fonts larger. Okay, all right. So I have T and C. Okay, so here, let me just put this objective function. Let me just, okay. All right. So here will be the constraint. 1, 2, 3, 4. Okay. Okay, I think I make this smaller row. Okay. Right. The coefficient, of the function, and also, what we have is we want to get the answer. So you may design this differently. Okay, let me just put this here. Okay, the coefficient is 7 and 5. Okay, here put this, the decision variable values. Okay, let me put here. All right, and then we have the constraint. There are 4 constraints, so I just make the 4 lines. Okay, and then I need the symbol for this one. Okay, and the right hand side, let me just put this one. Okay, so let me just make it a little bit bigger so everyone can see. Okay, and then what I should is just take the coefficient here. Okay, but here I just set the decision variable values first. Okay, and then okay, and then I have be careful if it is greater than or equal. For the less than, no problem, just put 3, 4. Those are the coefficient. Coefficient. And then here I want the symbol, and then I have 2, 1. Okay, this one is 2400. Make it a little bit larger. And then we have 1000. Okay, I hope that you can see this clearly, and then you can insert the symbol. This is just to remind you what symbol you work with, yeah. Okay,
Then equal, yes.
okay, and then yeah, let me just quickly. Okay, we have see
0.
0, 1. Okay, and then we have less than or equal. I will just demonstrate this quickly, yeah. 450, and then we have the t greater than 0. So if t greater than 0, because okay, for
Yes.
MATLAB it doesn't accept greater than or equal. For Excel solver it accept this, no problem. So you can put 1 0, and then the symbol here you can put this as greater than or equal. Okay, and then this is 100. Okay, that's all. Okay, the objective function. Okay, all right. So now what you have to do is you enter equation, yeah. You can multiply 7 with this, and then 5 with this, and then but the easiest way is use sum product, yeah. Sum product, and then you just multiply the coefficient, yeah, with the expected value of the decision variable, and then enter, yeah. So that will be the formula for the objective function, which is I multiply this objective function, yeah, with the respective potential solution, yeah, decision variable. Okay, now here I have to enter this yeah, I forgot to write down the formula for this one, yeah. So same again, you can use sum product, okay, and then multiply this yeah, with respective decision variable. It's just like multiplying the coefficient of the constraint with the t and c, the variables, yeah, the values of t and c. Okay, for this one you don't have to repeat that one, you just copy the formula, yeah. You can copy the formula, yeah. But first of all, you want this to be, yeah, the variables to be fixed. So that means you have this one. Okay. Okay. Did I miss anything? Hold on. Okay. Oh, that's okay. I think I can just okay. This one you can just highlight, but you must make sure that this one change. Sebenarnya tadi itu senangnya kalau ditukar je. Itu this one is the one that change. Okay. Right. So, right.
Okay.
Okay. Then the next thing is just you call solver. If you haven't installed it, just home option and then add the solver. Yeah, you can add it here. Yeah, sorry, file, option, and then you can adds in, and then you can Excel add-ins, go, and then you check solver add-in, okay, yeah. So that is how to get the data solver. So what you have to do is just call the solver, the formula, and then the solver optimization. So here you need to specify the objective function, which is this one, okay. And then we want to maximize, already a dot here, the selected, check, and then you highlight the objective function decision variable, sorry. And then for the constraint, you can do like together if they are the same, yeah, the same symbol, yeah. For example, subject to constraint. Okay, let me just put here because I cannot see the instruction. Okay, I add constraint. So here I can do together this one, yeah, because they are the same symbol, less than or equal. And then this one, yeah. And then I add this, I add another one, okay, which is this one, greater than or equal. This one here, okay. Click okay because those are the two constraints only, the two types of constraints. And then here solve using simplex LP. Yeah, make unconstrained variable non-negative because there are restriction here for this value to be non-negative. Okay, that's all. Yeah, finish with this. Check everything and then solve. Okay, and you can actually keep these answer reports. Okay, the report goes here. Yeah, and that's the answer in the box that I already allocated. Yeah, okay. So here, these are if I did not enter incorrect numbers. Yeah, I might have entered. What's the answer just now? Okay, what's the solution? Okay, 4040, the value of the objective function 320360. I got the right answer. Yeah, so that is how simple it is using Excel solver. Yeah, so basically you write the correct formulation and then you enter or design the Excel spreadsheet that you want to actually that to match the Excel solver requirements, and then you just specify all those values. It doesn't matter whether it's 20 variable or 100 or 200s. Yeah, but Excel solver has limitation. Yeah, it can actually solve up to 200 decision variables. Yeah, so not like MATLAB or other optimization solvers. So if you require to solve more than that, you have to install the premium version of Excel. Otherwise, you have to use Maple optimization, SAS optimization, Simplex, or MATLAB, or some optimization solver. Okay, I hope that is that give you some ideas about how you can easily solve the okay, hold on. You can easily solve the problems, or linear programming models. As you can see, what is written here, is based on the report, the 3 reports that I saved just now, the one that we obtain when we do the Excel solver. So we can interpret a lot of things here, So we can see slack, slack, that means, the resources are not fully utilized, So slack denotes the amount of unutilized resources. Binding constraints, that means the constraints that decide or as the one that dictate the optimal solution. Binding or not binding. Here you can see binding constraint, and not binding. Out of 4 lines that you draw, which one actually affect the solution or determine the solution. So the value of the optimal solution 320, 360, and the objective function 4040. Okay, besides that, we can actually go further in terms of sensitivity analysis. From the Excel report, you can see the range of optimality, which is the objective function coefficients lies within this. So if you want to modify your model, you can investigate what happened if you change certain things, related to coefficients of this objective function. So based on the allowable decrease and allowable increase, I can actually look at the range of optimality for table. If I want to change coefficient, make sure that my values that change should be in between 3.75 to 10, and the chair must be in between 3.5 to 9.33. And then, okay, this is just to explain further about the reason why we need to know that, because as you can see, changing the objective function coefficient within the range of optimality will not change the current coordinates of the optimal solution, and so on. So a lot of analysis can be done. Okay, here we want to check what happened if we do this, what happened we do that, and so on. Another sensitivity analysis is the right-hand side values. The right-hand side values, if you see here, is actually deals with the constraints. So this is the right-hand side values, RHS here. So you want to know, kalau tadi we want to actually change this value 7 and 5. This is the allowable changes. How about if we want to change the right-hand side constraint here? So these are the allowable increase, decrease that we can do for the right-hand side. So based on that, we can actually analyze. So we can see the feasibility of the right-hand side ranging. Besides that, we can also look at shadow price. What is shadow price? Shadow price is the effect of changing whatever units on the right hand side tadi, how does it affect the objective function, your objective function value, your profit or your revenue, yeah, or if you talk about maybe yeah, advantages that you will actually enjoy if you modify, yeah, the right hand side. So that is called the feasibility of right hand side changing, and what effect does it have on your objective function. So if you check here, there is a column on shadow price, yeah, shadow price. So you can actually estimate what happens if, yeah, if we are changing the right hand side, yeah. So here I put some analysis. How about if I increase that, increase this, and so on within the range here, within the range, yeah. Okay, so range of feasibility is here. So that means if I change this within the range is okay, and the effect on the objective function value can be looked at by analyzing the shadow price. Yeah, contoh, yeah, example. This is 2.6. That is actually good, positive value. You are maximizing. If you change here, yeah, something on the right hand side of this constraint, it will bring more, yeah, a profit. For example, if you are maximizing profit, and see the changes here. With the 2.6 times 400, it will generate 1040 extra, and so on. Okay, so there are a lot of analysis that can be done based on these answer reports of the Excel solver. But at the same time, when you are solving using Excel solver, there are some messages that can come up. For example, yeah, if you're dealing with infeasible problem, yeah, solver will denote here or put remarks, solver could not find a feasible solution. So that means no solution. Or the set cells do not converge. This is for unbounded problems maximization. For example, yeah, you cannot get the yeah, the solver to converge to any feasible point. Yeah. And you can also have alternate optimal solution. Yeah. Remember that alternate optimal solution means you have, yeah, infinitely many solutions. But how do we get this? You can do that by just changing certain thing. For example, first, look at whether you have allowable increase 0 or allowable decrease equal to 0, depends. Yeah. And then what you do is, if allowable increase 0, change the objective function to maximize. If you have allowable decrease equal to 0, change the objective function to minimize whatever value that you have there. Yeah. Contoh, this one here. Yeah. You carry out, you perform that, you can get infinitely many solutions, because what? If there is alternate optimal solutions, means you get infinitely many pairs of coordinates, yeah, for your answers. Okay. So you can also enjoy the luxury of, yeah, checking what happened if management decide this, decide that, and so on. So you get yeah, the problem becoming more complex and get more constraints and so on. You can enter this in the Excel, and then the same thing, you can get all this, yeah, report, yeah, answer report, where you are able to do the sensitivity analysis. Yeah. Okay. So these are the things that yeah, you can do with the linear programming solver. Okay. The one that I showed to you just now was just a simple problem. Yeah, simple problem. I'm just checking the time. Yeah, whether I have time or not. Yeah. Okay. That was just simple problem. 2 lines. Yeah, of constraints, or maybe up to 7 or 8 lines of constraint. But you can do more with Excel solver, or you can formulate larger LP model. Yeah, larger LP model. So how? And sometimes the way the functions are written in the objective function and constraints are not straightforward, like C1 x1 plus C2 x2 plus C3 x3 and so on. Not just in that kind of form. Yeah, sometimes it is written in summation form. Yeah, so you should be able to expand, yeah, to expand to see how many lines of constraints do you exactly get. So from that, you can see the matrix of the coefficient matrix, yeah, or technology matrix, yeah, the number of decision variables involved, and so on. Then you can design your template for Excel solver, yeah, the cells for Excel solver, so that you can solve the problem. Yeah, but first of all, you must know how to expand this model. Okay, what does it mean? For example, you have this for I equal to 1 to m, and so on. What does it mean by you having summation? Yeah, so here there's only one index which is j. Yeah, so the situation here is that A here contains I and j, but the summation only j. So that means you have two index or indices, but the summation is 1. That means you can only sum up with A, for example, j equal to 1, you have AI1, x1 plus AI2 plus x2, and so on. So in other words, you need to do this for each of the I. So that's why in the model, for all I equal to 1 to blah, blah, blah to m. Yeah. So that means if you got, or you notice that there are two indices, but the summation is 1 index only, so you know that it's expansion to row by row. Yeah. So the summation is for horizontal expansion and so on. So that means this is understanding how you actually elaborate the, remember that in journals or things, they don't write this type of formulation. Yeah, this is the long formulation. Yeah, they always write the compact version of the model. Yeah, so you need to be able to interpret what does it mean and how many lines of constraints you end up with, and so on. How many columns of decision variables? Because why in Excel solver, the columns of decision variables, you must know that. Yeah, and then how many, for example, you have A11, A12, and so on. Yeah, x1, x2, and so on. So that means decision variable, there are n columns. Yeah, but A11 here, this is going to be expanded downwards. Yeah, so that means based on the value of I. Yeah, so if I is equal to 1 until 10, then we have 10 lines, and so on. Okay, this is just a quick example of controlling air pollution. The instruction is quite lengthy, and so on. How do we end up with this? Yeah, this is the compact formulation of the model. How do you want to solve this using Excel? First of all, you write the complete formulation here without the summation notation and without this I equal to 1, 2, 3, and so on. So that's what you have to do. That's it. You have this, many lines here. Yeah, so remember that if the variables are not written there, that means the coefficients are all 0. Yeah, so you have 1, 0, 0, 0, 0. So that's how you enter it in the Excel. Okay, so the same goes with this example. Yeah, as you can see, we have these many decision variables. Yeah, and one thing that I have to remind you, if you are dealing with rational functions like this, remember that we are dealing with linear programming. So you must make, or you must transform it to linear equation or inequality. Yeah, so multiply both sides by this expression, so you end up having this equation. You can see that this is the linear inequality. You must get that first before you can actually come up with this formulation exactly. Yeah, so this is the complete model expansion. So you know exactly what are the coefficient of each of the variables. Then you can start arranging this according to column. So I am actually trying to show you the Excel solver is column oriented based on number of decision variables, and line oriented based on the expansion of the model in terms of the constraints. Yeah, so dah dapat macam ni, you got the patterns. Yeah, so you can see the patterns or the values that you need to enter. The missing one means the coefficient are all 0. Yeah, okay. So I will not show all of this, but there are various types of problem. This is scheduling meetings. You can also solve this using this one. As you can see here, this is just an example of how you capture the decision variables and then how to write down the values of the coefficients. This is the transportation problem. yeah, the transportation problem, we know that we want to send from the origin to destination or source to destination. Yeah, the compact version of the model looks like this. Yeah, but we want to solve the model in Excel solver. We need to understand exactly in terms of what are the coefficients and how it should look like. So this is the expansion of these two lines of constraints. Nampak tak? Two lines saja. Yeah, two line of constraint. But actually after we carefully expand this, we got these many lines. Yeah. So once you got this, you get the actual matrices to be input in the Excel solver, and you can solve this anytime. Yeah. And the solution can be interpreted as this. You can see, yeah, how transportation nature from the source to destination or origin to destination. And that's the answer. Yeah. Okay. And then we have the linear programming for transshipment. Yeah. What's the difference between transportation and transshipment? If transportation is from one point to another point. But if we talk about transshipment, there will be intermediate point. Yeah. So from A to B, but via C. Maybe in the middle is C. Yeah. So A, C, B. Contoh. Yeah. That is an example. Yeah. So this is the model formulation for transshipment problem. Look at here, the nature of it's written, the way it's written. You see, every time you see I equal to 1 to dot 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 M, this means the expansion is go downwards. Yeah, you have many lines based on different value of I equal to 1, I equal to 2, I equal to 3, and so on. If you look at here, 2 subscript IK, KJ, and so on, how do we write this? Yeah, look at here, K equal to 1, 2, 2R. So you need to interpret this or expand this first before you can actually write down the model. Yeah, for example, this one, yeah, model. Okay, and some other examples. Yeah, but I would like to, yeah, those are just example. I think you can do it easily. Yeah, but I want to talk about fundamental theorem of linear programming. Yeah, fundamental theorem of linear programming. So what are the basics of basic theorems in terms of linear programming? Yeah, so here we would like to see the importance of having these theorems as our basis for understanding whether we have the optimal solution, where should it lie, and so on. Yeah. And another thing is that we look at the association between primal and dual linear programming, how to transform the linear primal to linear dual, and how to apply duality theorems and complementary slackness theorem to get the solution. Yeah. Okay, so this is the basic concept. Yeah, we know that the linear programming should look like this, having the objective function, the constraints, and the non-negativity constraint. Okay, basically, if you expand it this way, okay, and we know that yeah, we are in standard form, it must be maximization, and then value of x must be non-negative. All the constraint must be less than or equal. It is standard form. Yeah, just now I just work out in any types of form. But if you want it to be in standard form, it must be less than or equal. Yeah, it doesn't have equal sign. It doesn't have greater than equal. If greater than equal, we transform it. Yeah. Okay, and BI must be non-negative. This is linear programming in standard form. Okay. So for it to be in standard form, yeah, if you are converting less than or equal to equal sign, you just introduce a slack variable. If it is greater than equal, minus a surplus variable at the, yeah, introduce a minus a plus variable, and then we can also add artificial variable if we have equality constraint or greater than or equal. Yeah. And then we can add the, for maximization, the coefficient of artificial variable. Remember, artificial variable is just dummy, yeah? It doesn't carry meaning in real world. And then we have this one and so on, yeah? Why is it that we introduce this one? This is particularly useful when you do simplex method, yeah? Okay, so the fundamental theorem has 3 properties, yeah? 1, LP has no optimal solution if it encounters infeasible region or unbounded maximization, for example. If it has feasible solution, then it has basic feasible solution. Basic feasible solution is the corner point or extreme point. Yeah. If it is bounded, yeah, then you can be sure it has optimal solution, and the optimal solution actually is one of the basic feasible solution or one of the corner points. Okay, so this is the fundamental theorem of linear programming. Yeah, so what can cause no optimal solution? If it is infeasible or unbounded with certain maximization, or it has feasible solution, then you can show that it has a basic feasible solution or corner point. If it is bounded, yeah, it has optimal solution, and the optimal solution lies at the corner point. Yeah, so I'm skipping the proof. Yeah, okay, so these are just to show you, yeah, about convexity, and also the convex polytope is the one that you have as feasible region for 2 or more variables. Yeah, more than 2 variables. Yeah. Okay. Now, this is I already stated. This is just another statement. LP infeasible, no feasible solution, optimal solution. Or if it is optimal, then it should be at the corner point. Yeah. So this is just breaking up the first one into 2, 1, and 3. Yeah. Okay. So if we look at this, yeah, we can actually look at, yeah, what determines for you to have a unique solution or alternate optimal solution. First of all, you must have the bounded feasible region, or you must have corner points. Then if you have corner points, definitely, yeah, you may be able to find solution. Yeah. Okay. And then if you are finding by exhaustive search, investigating one by one, yeah, how many potential solutions that you must investigate before you can find the optimal solution. So the formula is given by a combination formula, n choose m. Yeah, for example, for n equal to 10, yeah, and m equal to 5, that means 10 variables, 5 constraints. It's already 252 solutions or feasible solutions in the feasible region. So in other words, what I'm trying to say is that if you have many variables and many constraints, it is not advisable to do this manually and list down all the solution and evaluating the objective function value. Yeah, you should use optimization solver, be it Excel, MATLAB, or whatever solver. Okay, now let me just check the time. Okay, I have a few more minutes, but maybe I have to use yeah, less time for the integer programming. Yeah. Okay. Now let us look at the concept of duality. Yeah. For any linear programming, the original one given to you, which is called primal, you can actually see it in different perspective. We call it dual. Yeah. In other words, if you have a maximization LP, you can actually formulate the dual, which is a minimization problem, or vice versa. Yeah. Okay. So what is the interpretation? Sometimes the management would like to see how much profit does it give you if you produce this many X, many Y, or many X1, many X2, many X3. The combination of this production, how much profit do you gain? But at the same time, the management can look into the cost, yeah, to produce these products. Yeah. So that means you want to see it in the perspective of minimization of cost, and also maximizing revenue or profit. So that is why we have the dual and primal. Yeah. So the best thing about it is that if optimal solution occur, the objective functions of both primal and dual are the same. Yeah. So let us look at the relationship here. Okay. So I'm sorry that yeah, the number actually move. Yeah. Okay. So what we have here is just to compare between primal and dual. You can see that the C here, also C here, the B here, and the B here, and the A and A here, they are related. For example, the coefficient of the objective function is actually the right-hand side of the dual. Coefficient of the objective function of the primal is the right-hand side of the dual. And the right-hand side of the primal is actually coefficient of the dual. And for the matrix A, you just need to transpose it. Yeah, where one is concerned with the variable X, the other one concerned with variable Y. Yeah. Okay, so this is the transformation of the dual. It is actually very simple if you follow these rules. Yeah, okay. Because these are the relationship between those two. I mentioned just now, the coefficient here is the right-hand side there, and so on. Yeah, okay. This is actually, yeah, going to guide you, and these rules are going to guide you in the transformation of primal and dual. This is just summarize it in the table, and now I am showing both, yeah, where these numbers occur in both primal and dual. These are the relationship, and you can use, yeah, this relationship in order to make interpretation. Yeah, so this is the table of conversion. Yeah, conversion table for you to easily transform from primal to dual, dual to primal. As I said that Z and W here has its own function. For example, one is cost, the other one is revenue. Yeah, or one is working hours, the other one is salary. Contoh, yeah. Okay, so how to transform this? Okay, I am just following this table using this as guidelines, and then I transform it, I get this one. Yeah, you may want to try that once you get these notes. Yeah, okay, and then this is an example of application problem. Yeah, where you can actually, yeah, interpret. Yeah, here also, yeah, this is an example where you can see the relationship in terms of the shadow price and the cost. Yeah, okay, so I hope that you will be able to use this, yeah, and look at the relationship, yeah, by using duality. But most importantly, other than fundamental theorem of linear programming, yeah, since we have primal and dual just now, there is one theorem called weak duality theorem, and the other one is strong duality theorem. Yeah, so this is to relate the value of the objective functions of both primal and dual. Yeah, and there's also another theorem, complementary slackness theorem, where you utilize the information that you know about primal and dual. Right? For example, if you want to find dual, you get the information on primal. How do you utilize that to get the answer for the dual? Or if you get the information on the dual, how to get the solution for the primal? Okay, so this is the relationship. If you have optimal solution for the dual, definitely there will be optimal solution for the primal. If the primal is dual is invisible, then you can guarantee that the primal is unbounded. If it is dual is unbounded, primal is invisible. But if you have both primal and, yeah, invisible, that means you will have this as invisible. Yeah. Okay, so these are actually the proof of the strong and weak duality, and the questions that you may want to ask yourself. Yeah, and last one, this is interesting in terms of complementary slackness theorem, which, as I mentioned, if you know about the primal, can you get the answer for the dual? If you know about the dual, can you get the answer for the primal, and vice versa? Yeah, so I hope that you can check on that one. That's the end of part 3. Okay, so since we don't have that much time, I will just
Yes,
continue.
Doctor.
Yeah, with the integer programming. Is it okay?
Just
Just a little bit introduction only.
yes, introduction only.
Yeah, introduction. Yeah. Okay, just to note the difference, let me just use this one, yeah, as a note. I know that I will not have enough time actually. Okay, this is just to show you, yeah, the difference between LP and IP. Linear programming and integer programming, what's the difference? Okay, so integer programming, as the word mentioned, you expect that you want to solve a problem where you expect integer solution. Yeah. For example, if you talk about number of cars, number of machine, number of people, of course, you cannot use linear programming because you cannot get the answer as having decimals or fractions. Yeah. So that is the reason why you need integer programming. Yeah. Okay. So here, the types of integer programming can be pure integer where you have all integer solution, or mixed integer where some of the variables have real numbers, yeah, while the others may be binary or integer. Or you can have purely binary, that means all the answers are or decision variable values are 0 and 1. Yeah, okay. Now, why is it that we require integer programming? Yeah, I mentioned to you just now that for linear programming, yeah, you cannot simply round off the number to make it integer to mention that okay, this is the solution. Yeah, because why? There is a possibility if you round off the value or the point, yeah, after rounding off is becoming outside the feasible region. In other words, it become invisible. Or if you round off the value to become integer, suddenly it is going to produce, yeah, a solution which is lower than the expected optimal solution. Yeah, but sometimes when you are lucky, you get optimal solution. So in other words, rounding off linear programming solution is not the best approach to get the answer or of integer values for the decision variables. Yeah. So let me show you here. When we draw the feasible region for integer programming, nampak di sini, ya, lihat di sini, there is an extra information for the non-negativity constraint. Beside the non-negativity constraint, you must spell out. If you want the answer to be integer, then it must be spelled out integer. Yeah. So for example, if you have this as the answer, this is the type of machines, yeah? You cannot accept answer of 2 point something machine, 5 point something machine. You cannot buy that fractions of machines. Yeah, you cannot have that. Therefore, you might think of the best solution is just round of the value. Yeah, but it doesn't work. Yeah, if you want integer, you must use integer programming methods. Yeah, which is if you round off, you end up having, yeah, for example, yeah. Yeah, if you round off, the answer might not be in the feasible region, for example. Yeah, so here, if you look at, if you round off 2 and 5.55, you end up having, for example, 2 and 5, which is here. Yeah, if you if you take some other values, you may get different values. Yeah, so it depends on how you round off that. Yeah, but here, this is the exhaustive search for the answer, which is enumeration method. You can always look at all dots, enumerate this, evaluate the objective function. This is the classical method. Yeah, that is, you do the manual work of evaluating. Yeah, it works for small problem like this. Yeah, but if you have 100 dots there, you don't have the time to evaluate one by one. Okay, that's one thing. Yeah. So enumerating is not the best approach, okay? But the best approach, of course, the easiest one is just use Excel solver. You can get the answer, yeah? But when you are using Excel solver, please make sure that if you are solving integer, yeah, you must make sure that, for example, if I want to add constraint here, yeah, you need to make sure that you write int. That is for integer answer. Yeah, you must highlight all decision variable, you click integer. Or if the answers to be binary, you click bin, yeah, for binary and so on. So that's the only difference when solving, yeah, integer and also linear programming. Yeah, that is specifying what kind of values should appear for decision variables. Yeah, so these are the example. Nampak ya di sini, yeah, it specify the values of the decision variable to be integer. Yeah, okay, that is just to give you the answer. For example, here, instead of just now 2.22, 5.55, if we round off, we get 2 and 6, for example. Where is 2 and 6? If you look at the graph, 2 and 6 is outside here. which is not feasible. Yeah, but the correct answer is after we use the solver, the answer is 1 and 6. Okay, just to show you. Yeah, and there are a lot of various kinds of integer programming, pure, and you can have the pure again here. These are all the solutions for this. And then look at the beauty of having Excel solver. You can get alternate solutions. You can get many solutions here. You can produce many sorts of solutions. So you can use it as your timetable, scheduling this personnel. Okay. And we can also have binary, integer programming for portfolio, investment, capital budgeting, and so on. And we can also use the fixed charge, mixed integer programming. So here you can see that the number of variables can be more or larger and larger, and so on. In other words, as I said, that Excel solver can solve up to 200 decision variables. Okay, before I stop, I just want to highlight to you, that actually, when I want to do this, in this lecture, there are other topics under linear programming which are equally important besides the fundamental theorem, which are the simplex method. I mentioned about Danzig, the mathematician who actually come up with the simplex method to solve LP. That is also an important topic. Besides simplex, we also have revised simplex method. Simplex method, which is using table or tabulated, table oriented. The other one is based on matrices oriented, which is revised simplex method. So maybe you can look at those, these two methods. Well, of course, the fastest is computational, optimization solver. Besides that, I want to tell you that for mathematical programming, beside the optimization solver, you can work on the solution method. So basically, if you're given a mathematical programming model, you have two options. One is called exact method. Exact method is where you use the classical approach like simplex, dynamic programming, or you use all those, but for simplex method, branch and bound, dynamic programming, and so on, the problem is the dimension. So as the dimension gets larger, maybe it takes longer time to produce the solution. So for small and medium problems, exact method which guarantee global optimum are good. But if you work with 1,000 decision variables, 100 nodes of network flow problem or transportation problem, it is not advisable to use simplex method or to use just now enumeration method. You must work on approximation method. So we have exact methods, which are simplex method, branch and bound, all those classical methods, versus what we call the approximate methods, which may or may not produce global optimum, but it produce reasonable solution, feasible solution, within a reasonable computational time. So what are the approximation method? It is where you don't get the global optimum, but you get somewhere near there. So here, in other words, good enough. Here you get to use heuristics and meta heuristics. There's another topic which is very interesting. So nowadays, if you talk about optimization, you cannot run away from computational algorithms that use heuristics and meta heuristics. So besides learning about simplex, and so on, and also the solver that we work on for small number of variables, they get the global optimum, but work nicely within reasonable time for small problem. Integer programming, if you have large number of decision variables, if you use the Excel solver, it takes many hours or a long time, yeah. Dulu lama lah, yeah. A long time to get the answer. But nowadays, as the computer get so sophisticated, faster, it may actually reduce the time, yeah. But previously, in order to get global optimum for integer programming or mixed integer or binary integer, it takes long time, yeah. You run it for many hours and so on, yeah. But nowadays, maybe because of the computer of powerful, you can get the solution faster. So we have exact methods and approximate methods, yeah, especially for integer programming, binary integer, mixed integer, or the pure, yeah. And the one that I cannot present to you this time is the goal programming method, yeah, when you have single versus multiple objectives. Single objective, very simple, yeah, like just now, if you are able to expand the model, you work it out in Excel solver or some other solver, and you get the answer. But how about if you have multiple objectives? You have maximized this, minimize this, but subject to the same constraints. Then you must use goal programming, and I don't have time to cover that, even though I have the notes here, yeah. So I did not cover simplex, reverse simplex, goal, yeah, dynamic programming. There are a lot of topics in mathematical programming. With that, I conclude my presentation. Thank you very much, everyone, for your attention.
Masya Allah. Thank you very much, Dr. Adiba. I enjoy listening to your lecture. I'm sure the students and participants are also. We can stay whole day just listening to the lecture. Very interesting.
Thank you.
Especially you also include tutorial on how to use the Excel solver. I think students love that so much. Maybe we can invite you again sometime too.
No problem. Yeah. Is there any questions here?
Any questions, students? Does fuzzy logic have a good chance in linear programming optimization?
Oh, okay. Yeah. Fuzzy is good because why? Quite a number of my students actually they have the mathematical programming model. Yeah, sometimes it is mixed integer, or sometimes binary integer. Depends on the problem. Yeah, for example, you talk about portfolio investment. Yeah, investment or stock problem and so on, or maybe scheduling problem and so on. You can actually convert it to fuzzy programming. Yeah, you can actually convert the mathematical programming model. Yeah, embedded in terms of fuzzy, yeah. So my students have done that. Actually interesting, yeah. You can think of merging the ideas of mathematical programming and also fuzzy, yeah. It is interesting. You can do that actually.
Yes. Okay.
Quite a number of my students have solved problems using fuzzy logic. For example, that one was for the cross-docking problem. Cross-docking means, for example, we have supermarket, the distribution warehouse. Yeah, we want vegetables and all the supermarket items be bulking or debulking within the cross-docking center. It must be done faster, so we must be able to have a very good algorithm to make sure that we can do the mixing faster, so that the trucks can move faster, because cross-docking require that the items to be delivered within the same day, for example. So we must be able to use fuzzy logic to estimate the waiting time, kita punggah apa maksudnya, taking out the items from the truck and later we put items in the truck. So we must be able to use fuzzy logic to estimate. One is the capacity or the amount of items, the time taken, for example. It is actually interesting to use it.
Okay, Fadil. Anyone else? Thank you. Any more questions, students? So I think you have a wide.
Okay, there's one question here.
Many applications. Okay, another one. What's the connection between calculus and linear programming?
Okay, all right. when I talk about the first part just now, I talk about constraint and unconstrained optimization. Yeah. So if you look at the constraint optimization, that is actually basically the same items that we are dealing with. Yeah, we have minimize, maximize certain things subject to constraints. Yeah. The thing is that in calculus, we use the Lagrange functions and we use partial derivatives to get the answer. Yeah. But in mathematical programming, yeah, we state it the same model, but the approach is different. In using Lagrange, what we do is we rewrite it in terms of Lagrange function and use partial derivatives. But in linear programming, we simply just use the idea of, for example, yang Excel solver tadi is actually simplex method based on simplex. Yeah. So when we use simplex, it means we use the approach that was done in linear algebra. In linear algebra, we use row operations. Yeah, we reduce the matrices in order to get the solution. Same technique, but it is just appearing differently when you use the Excel solver. Actually, the Excel solver or the whatever solver optimization, they use simplex as the basis, yeah, which is actually stem from linear algebra, which is in other words row operations. Yeah, but in terms of concept, the formulation of the model in calculus and in this here same. We have the objective function to optimize subject to constraints.
Yes. Any more questions from the audience? Is that enough? So yes, I think the students gain a lot of better understanding, I think, of linear programming, and more. I think this is a one semester material that you
well, yeah, maybe one semester. But actually, I just highlight the items, but I did not go through all these. There are actually many things here there within one semester. Yeah, even linear programming can be one semester.
Yes,
but
this is
normally for degree we limit it to linear programming and just basic on the fundamental theorems. But for master's degree, we blend it linear and integer.
So you have master and PhD program in this area?
Actually, we do this by research, by coursework. The one that I told you in mathematical programming is actually a master's program by dissertation. That one is for coursework. Yeah, so there is a course on mathematical programming. Yeah, where the students, once they take that particular course, it's easy for them to do research project because they know how to formulate the model and they are able to solve it either using solver, or they can code their programs, yeah, their heuristic or meta heuristics or whatever approach that they want to do. Yeah, nowadays some people can do using Python programming in order to get the solution.
Okay, I think that wraps up our lecture for today. Again, many thank you to Associate Professor Dr. Adibasu Aib. We give an applause for her lecture.
Thank you for everyone for paying your attention, listening to me.
I'm sure some students will be inspired with your lecture and your career, professional. Hope they will pursue also further in the mathematics area in operation research. Okay, so Ms. Mega, I return back to you.
Okay, thank you so much, Mrs. Ratna Herdiana, for guiding us through the discussion session. And also thank you to our speaker, Dr. Adibasu Aib, for delivering very insightful presentation and wonderful discussion. Okay, now we are going to our next agenda, which is giving certificate and thank you notes to our honorable speaker, Dr. Adibasu Aib. by representative of Mathematics Department, Mrs. Ratna Heriana, MSc PhD. Okay.
Okay, on behalf of the Mathematics Department and the Faculty of Science and Mathematics, we are pleased to present you. This is a token of appreciation to Associate Professor Technologist Dr. Adiba
Thank you
Sued.
so much.
We will send you the certificate with the signature. This is
Okay.
temporary.
Yeah, in return, I will share the slides with you.
Yes. We
Okay.
will be thankful if you can share the slides, the material. Yes. Thank you again, Dr. Adiba, for a
Welcome.
very interesting and wonderful lecture this morning.
Thank you to our MC, also Dr. Ratna. Thank you, everyone.
Yes, you have any closing remarks or any remarks, Dr.
Yeah.
Adiba?
Yeah, I'm so grateful actually being invited to this session, because before this I think I have not heard about Diponegoro. Yeah.
Oh, yeah.
I have heard about other universities. I have actually dealt with Universitas Lampung, Pajajaran, Narotama, Bandung, and few others. But I have never heard Diponegoro. So first time,
Okay.
and I think it's good to know, to know more people, and then it is very interesting actually to be able to share my little knowledge. Actually,
Yes.
sometimes the minute you present, the more things that come. Yeah, even though you say that this is eye-opening to some people, but at the same time, I start thinking about how about I do this part here. Maybe I
Yeah.
haven't got the time to do that part, for example. So when I present, I start thinking about, okay, what can I do next, for example. So it is very interesting to meet people, to be able to share. So I hope that this is not the last time that we communicate, Dr.
Yes, of
Ratna
course.
and Miss
We hope we
Mega.
can invite you.
Jangan
We can make it a
segan-segan
series.
lah itu please contact us, communicate with us,
Okay, thank
maybe
you.
it's time for you to present to our students, or maybe come over to Malaysia and I come
Yes.
over there.
Yes, we can send students to you maybe next time.
Okay.
Okay, Miss Mega.
Okay, thank you, Mrs. Ratna Heriana, for delivering thank you note, and thank you for Dr. Adiba delivering the remark. Ladies and gentlemen, finally we are going to our last agenda, that is closing. Let's close our program by reciting Hamdalah together. Alhamdulillahirabbil alamin. I would like to say thank you for all participants and guests for attending today's visiting lecture, and thank you for your active participation and also attention during our event. I am your Master of Ceremony, representing the entire committee. Apologize for any mistreatment presented in this event. I would like to say thank you again for all participants, speaker, and moderator, and don't forget to attend the next visiting lecture on 17 May of 2023 with other interesting topic and also speaker. See you again at next visiting lecture. Thank you very much for your nice and kind attention. The last I say wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi. Bye, Doctor.